Good afternoon, everyone. And I think before we start off, because the internet is intermittent, you can start cloning the repo, and by the time we get into hands-on, I think everyone should have most of it there. It's github.com/unnati-xyz/intro to deep learning for NLP.
Let me create a shorter URL for you.
Oh, yeah, okay.
Yeah, so it's small.cat/pig, and I'll redirect to the repository.
Yeah, I'll just redirect you guys there, and you can start cloning the repo. Meanwhile, we get started. Yeah. Hi. I'm Nischal, and he's Raghotham, and we are co-founders and data scientists at Unnati Data Labs. Okay, I'm covering this. Okay. At Unnati Data Labs, and we do data science consulting for various companies in Bangalore. And today we are here talking about introduction to deep learning, and we'll see how deep learning is being used in the field of natural language processing. So before I get started and start going deeper, how many of you here know what deep learning is all about and neural networks? Okay. Yeah, then I might bore you guys a little bit because I'll be talking about some introduction on what deep learning is and how it started and what's the inspiration. So today's agenda is we'll start looking at motivation to learning, introduction to artificial neural networks, an MLP, and then hands-on on the MLP, and we start looking at how deep learning is being used in the field of natural language processing. First, okay, so before we go into deep learning, how many of you here are familiar with machine learning? Wow, okay, awesome. Okay, so this cartoon probably explains it all, right? And there's a boss who says an internet is telling him that he might be dumb enough to enjoy extreme sports, and he goes to his employee and he says, the internet's trying to kill me, and he says, this is what we call data science, right, or machine learning. Okay, machine learning is extracting features from data to solve predictive tasks, right? And what are the use cases? So all of us have used Amazon, all of us use credit cards, and machine learning is widely being used to build recommendation systems. It's being used for forecasting. It's trying to capture anomalies. And yeah, today we're not here to talk about machine learning, so this is what it does. The reason I bring this up is we'll break the words into two halves. What exactly is learning? Anyone? What is learning? Like when someone says it's machine learning or they say talking about deep learning, what exactly is learning?
Extracting rules.
Sorry?
Extracting rules.
Extracting rules for?
Solving a problem.
Solving a problem, right? So let's go even more trivial. How many of you can recognize all the digits here? Everybody? Yeah, all of us can, because irrespective of how 5 is written or 7 is written, we can understand what this is. But now if I were to make a system understand this and ask the system, if I give you a number, can you tell me what it is? It probably can. So this is how you do it. You have an input, you build a mathematical model, and then it gives you an output. Now, then you start using functions and you compute whatever works, and you start using the ones that work for you. So here the simplest one would probably be something like k-means, where you're saying if I give you a number, give me the one that it's most similar to. But the problem here is, now there are so many different ways you can write a number, and if you were to put all of them into one single model, the model starts to break. The reason being, hard-coded rules are very brittle. The model in turn is not actually learning. It's just understanding the rules that you've provided the model, and it's trying to show you results that might not be very accurate. And yeah. So let's look at what is the biological inspiration for learning, right? And okay, so how many of you guys here have heard of the terms cognitive science or neuroscience? Okay, so before going there, how many of you have seen small kids grow up? Right, everybody. So I think the biggest thing that all of us try to do before we even understand any of this is we try to think only mathematically or in a computational way without even trying to understand what is the inspiration for building neural networks, what is the main idea why neural networks work. And the biggest influence has been biological inspiration, where neural network is nothing but we're trying to recreate the neurons that are triggering through our mind. And a neuron actually consists of a soma, which is essentially your mathematical function, and then there's inputs that are coming through your dendrites, and the outcomes are going through the axon. So in our body, we are able to assimilate all of this at such high speeds with so much accuracy, because there are about 10 to the power of 11 neurons that are working right now as I speak, probably more because I'm on stage, and each of them are connected to the other neurons, like the 100,000 synapses that go out of each neuron. Okay, so the next biggest question we have is, as we are growing up, we've learned so much, and it's fascinating that we can remember so much of it and base our decisions on top of that. So how do we actually detect information, and how do we store it? And using this, how does it influence our recognition? If you've seen kids grow up, even before kids hit school, they're already talking grammatically right sentences. They're able to detect the difference between drinking water and the ocean, and they know what's what. And you never really, you don't sit with a kid and tell them, you know what, this is how you should speak, these are the words that you need to pick up. But the kid's already learning, and the main reason is it's looking at its surroundings, it's trying to understand what people are talking about, and internally the learning mechanism kicks in, where it knows that it doesn't know that there's grammar associated with its speech, but it knows that this is the right way of doing things. So let's take a little more deeper on how our visual cortex actually works, and how you guys are able to see this, and you're not scared or that this is a demon or something that's coming out. The main reason is, first, there's a hierarchy that's in place and that we're not aware of, because the neurons are so fast and they're working at such speeds that you don't really think your mind's actually doing this. But what actually happens is, your visual cortex breaks down systems into first identifying the edges, and once the edges are identified, it tries to understand the position and the place of an object through its shape, and slowly differentiates if it's a cat or a dog. But it's so fast that you don't really see that this is happening. So in short, hierarchy is very important, and the complex output comes from building small things first. Yeah, and there are examples of learning. So let's take a very simple example. Right, two curves on a plane. So if I were to give you guys a point, how would you classify the point to be on the blue line or the red line? How would any of you guys do it? Sorry? Distance from?
To the nearest point on the line.
Yeah, so you would probably have a threshold. You would have a threshold. Anything that's greater than 0 is on the blue region, and anything that's lesser than 0 is on the red one. How many of you are happy with this? How many of you are happy that if you have a system that does this, you're okay with it? None? Okay. Let's make it a little better. Let's try to give it shape. Right? And we say anything that is of this shape that comes in, and I show it in the blue region and the one in the red. how am I actually doing this? Any of you have any idea how this happens? How we have a model that can sit against the lines of the curve?
You mean a model in our heads?
Y- yeah,
Mathematical.
mathematical, yeah.
Mathematical.
Yeah. So instead of going, so the simple thing is we are able to linearly separate two regions, and how do we do that is we transform it to a higher dimension. In the sense we look at a dimension where we can linearly separate two things, and we say this is the model that fits, and this is what I'm going to use. Now, this works, and this is beautiful because it's in a two-dimensional space, and you can solve this. But in a real world, okay, so this is a visualization of, okay, I don't know why the GIF's not playing.
That's a GIF.
Okay, I'm sorry, the GIF's not playing, but what it tries to show is, it tries to show how if you have two curves, and the visualization of how you can linearly separate them. Now, what will you do with this? It's no more in two dimensions, it's no more on a XY plane, and this really becomes very hard to solve. Not that it can't be solved, but this is how our real world problems are. So what we learn from books is most of it's just on an XY plane, and you try to build models and mathematical formulas around it. But in a real world, when you start working with things like this is when things become more and more tricky. I'll not get into how you can solve this. There's a beautiful post written by Christopher Ola on how you can solve this, and he's given a lot of neat descriptions on how you separate them and what is the process. That's more about the biological inspiration and why we have neural networks. Raghotham is going to talk about how neural networks are built and what are the building blocks, and then after that we look at MLP.
Yeah. So Nischal showed us how the biological inspiration of artificial neural networks are. Am I audible? Yeah? Okay. So let's try to use the same thing and model our simple neural network and see how artificial neural networks actually work. What are the building blocks of that? So before we go there, a simple question. A zebra, sorry. Just move this side.
Yeah.
Is it black with the white stripes or white with black stripes? Black and white stripes. Okay, and what do you guys say? Do you think it's right? Black with white stripes or white with black stripes? White. So, no, she's right. It's black with white stripes. Yeah. Okay. So, going back to the building blocks of artificial neural networks, we saw the soma dendrites of our brain and how it functions. So we'll model our neural network also in the same way. So we have the neurons. All the circles here are neurons. And then each neuron is connected to other neurons via a connection, which was basically the axons and dendrites in our brain. And every neuron does some function, and this is called as an activation function. So it receives an input or a set of inputs, does some transformation, and gives you an output. Yeah? And to do any complex set of activities, let's say recognizing a digit, a simple neuron cannot do and learn everything there. So what we do is we build a cluster of neurons and connect them together. So this is how a simple neural network looks like. You have a set of inputs, and then you have a hidden layer which has activation functions, which actually transform the input to output and give you the output here. Yeah? So this is actually called a feed-forward network. So the input is always flowing from, the data is always flowing from left to right, but it never comes back. There's no feedback loop here, if you see. So this is called a feed-forward neural network. And you can have multiple set of hidden layers. There can be two or more, not just one. So what are these activation functions actually? So you get an input, you transform, you have a mathematical function, you transform it, and it is an output. So there are different activation functions out there, and the first or the earliest one is the perceptron. So here you define a threshold, and any input value below the threshold is 0, and any value above the threshold is 1. So it does simple tasks. It will just tell you 0 or 1. And then we have sigmoid, or the logistic function, which most of us are aware of. You just get a value between 0 and 1, and you can use this as a probability. And let's say you want to do a multi-class problem. Then you don't have one output, but you have multiple outputs. Let's say you have a photo, and then you want the neural network model to tell you if it is a cat or a dog or a sparrow, something. So you have multiple classes there. So that is when you use softmax. It is basically a generalization of logistic regression or sigmoid. Then the next one is a more simple one, rectified linear unit, or it's called as ReLU. So what you do here is you have a threshold. Any value below the threshold is 0. Any value above the threshold is the input value itself. So if our threshold is, let's say, -2, and the input is -3, the output will be 0. And if your input is 4, the output will be 4. So that's about ReLU. And again, we have a generalization of ReLU as well, which is called max out. So if you see here, let's say if we want to figure out what is the shape of the V, use multiple ReLU units and then figure out how it actually works. So it's just a generalization of ReLU. So now that we have the basic building blocks of neural networks, let's see how we can learn using the neural network models. Yeah. So there's a concept called backpropagation, which helps the neural network model to learn, and this is it. Yeah. So there's a lot of math, right? We don't want to go there and figure out what. So I'll just subtract the math part and try to explain how it actually works. So what happens in a feed-forward neural network is you have inputs, and every input is connected to the hidden layers in the front. And these connections will be assigned weights. So the input to the hidden layer will be the input and the weights. So when you start the neural network model, the weights are randomly assigned, and then you start your computation. And this hidden layer can do any sort of activation function. It can be a sigmoid or tanh or ReLU. So it will use the weights. So it will multiply the weights in the input and sum all of them and give you the output. So what actually happens is, let's take this example. We have two inputs. We have a hidden layer, and we have an output. Yeah. So initially, we have random weights, W1, W11, W12, W13. Yeah. And they are randomly assigned. And then you simply run one forward pass of it, and then you get an output, which is y hat. Yeah. And obviously, this is erroneous because the weights are randomly assigned. So we have an error, which is E, which is the difference between the actual and whatever we have got now. And our job is now to minimize this error. So how do we do this? Anyone wants to answer?
Differentiate.
Sorry? Different shape.
Differentiate.
Yeah, differentiate. Yeah.
Oh, sorry.
Yeah, right.
Okay, now, like what do you, like, yes, you differentiate, but why are you differentiating?
So how do you go? Do you start from this x1 or x2, or do you do something else? What do you do?
You go down the error gradient until you reach the mean.
Right. So what you try to do is you have the error. So I'll simplify it a bit and try to explain it. So you have the error. What you do is to fix this error, you adjust the weights in the previous connection here. So you make W21 as W21 bar. And how much you have to adjust depends on your gradient descent. Yeah. So that is exactly what he was referring to. You differentiate, and you know how much of W21 you have to change so that your error is minimized here. And when you do that step, obviously you'll have to fix your first layer as well. So what you do is you go back one more layer and then fix the weights for them too. So W11 will become W12, etc. So this entire thing of one forward pass and backward pass is called an epoch. And this is where the actual learning happens. So after one epoch, you know what, you do one round of correction and you run the epoch for multiple times, let's say 10 or 100 depending on the problem. And this is how it actually works. So this is all about learning in neural network. This is the backpropagation algorithm. There's a lot of math involved to it, but our interest is not that today, so let's move on. So basically what you do is you compute the gradient, the loss function, and you backpropagate, fix the weights in the previous connection, and then you run it multiple times.
How many of you here were present for the ping pong AI thing that was happening? Yeah. He was talking to you guys about using mini batch and gradient descent. So internally what the neural network was doing was whenever the ball used to miss the bar, it knew that that was an error. And the learning was how do you adjust the weights for the movement so that it starts getting a positive score. So that's what he was talking about, the loss function and how the weights get adjusted. And the weights get adjusted through backpropagation.
Yeah, and to do that you need to do gradient descent. So let's say this is our error function, we are on the top, we need to minimize it. So it can be of different types. Let's say it's a hill and valley approach. There might be multiple, depending on where you stand and where you start to descend, you can go to different directions and end up at different places, right? So gradient descent helps us do that. And the problem is you never know if you actually go to the bottommost part of the valley. There's a concept called as local minima, where you don't know if that is actually the minimum, the global minimum. You get into this pit and you think that is the minimum, but actually there is a different minimum at the global scope. And yeah, gradient descent was what we use. But then you can, to use gradient descent, you'll have to use the entire data set. And in case if you're doing an image classification or something, you can't fit them all into your RAM and memory. So what you do is you take batches of them. You take, let's say, 100 or 32 or 64 at once. You batch them, and then you do a gradient descent on them. So I take first 64 set of data. I do a gradient descent. I take the next 64, again do a gradient descent. So this is called stochastic gradient descent or mini batch. And when the batch size is 1, it is called an online learning. So yeah, so let's go to multi-layer perceptron. So in a multi-layer perceptron, this is a feed-forward neural network. You have multiple inputs. You can have multiple hidden layers here, and then you have an output. And generally, a sigmoid activation function is used in multi-layer perceptron.
Okay, I think before we proceed further, how many of you are on the same page? And if you have any questions, you can ask away.
Yeah.
Are we good? Like, do we? Yeah, sure. Yeah.
So, is it important then with the choice of cost function? Does that make a big difference with how effectively you can train? Like, if you might have some options, like one of them was simply convex, and then that's kind of fairly straightforward to solve. But then you might choose another cost function which could, you can't really solve it
Yeah.
straightforwardly.
It again depends. Generally we try out different cost functions and figure out. So what works best for you might not work the same for others and the problem we are solving. So we need to actually try it out.
Yeah.
You said you chose the weights at random for the axons.
Yeah.
How do you choose what type the nodes are? Or is that random as well?
Oh, no, the nodes, okay. So you know what the inputs are, right? The nodes that you actually choose and build are the hidden layers.
Yeah, in the hidden layer.
In the hidden layers. So in the hidden layers is where your activation function works, and you configure it. So you can have multiple hidden layers, and each hidden layer is of one single activation function type.
You
So
can
if
have a mix and match.
Mix
of
and-
it. One hidden layer will have all of them as sigmoid or ReLU.
the other one could probably have a perceptron or a tanh. So you can have multiple layers of hidden layer, and each of them have multiple neurons in them. And in one hidden layer, there's one single activation function.
And I apologize if this is really beginner. How many nodes do you choose in your hidden layers? And is that related to your domain and your range, like your input and your output? And then has anyone tried mixing and matching to like get different types of nodes in a layer? Or is that pointless?
It's your problem defines how much of nodes you need in a hidden layer. There are some, I wouldn't say standards, there are some hidden layers that people follow of how big the hidden layer should be. The biggest problem with having more than X number of nodes is the computing capability, because the moment you add more and more nodes, your computational time starts growing. So you need to really know what you're trying to solve and what your hidden layer is actually doing.
Thank you.
Yeah.
What are the range of values for the inputs and then potentially the outputs as well?
So the input can be anything. It depends on your problem, right? So it can be a image classification. So your input.
I mean literally. So take x1.
Yeah.
Is that anywhere on the real line, or is it only positives, or is it 0 and 1?
It can be anything. So let's say we'll actually do a hands-on, and maybe you'll understand it better. So we'll take a data set from Kaggle, the auto data set, where you have 93 features and you have one target or label field. So you feed all the 93 as input. So you have 93 nodes there as input.
So what type is one of them?
It can be any. Yeah. It need not. So your type defines.
Presumably it's a real
Yeah.
real number. Or
Yeah, it can be a real
It can
number.
be a real.
right?
Yes.
So okay, cool, thanks.
Yeah.
Yeah.
Yeah. Single layer.
What is the advantage of this over multi-class regression?
No. Okay. So this is not an advantage. So what we are trying to show here is there are multiple hidden layers, and then there's.
I mean, when there is one single.
So yeah, this is just an example, but depending on your problem, you can have single output or multiple output. If your problem is a binary classification, then a single output will just do for you. But if you have multi-class problem, then your output will be multiple nodes here, not just one.
Yeah, I know that. I was just wondering how it compares to logistic regression type of approaches, since the function can be a sigmoid function as well, which is the same one as using logistic regression.
So,
Yep.
so there it is just one single logistic function, right? But here you have
Multi-class one would be
That's a softmax. Okay, so what actually happens is your outputs are different. So the dimension of your output is different. So in terms of like if you would build this neural network to do a multi-class, let's take a simple problem. So if you're given a name and you want to figure out the gender for the name, it's binary classification. It's yes, it's male or female. But if you were to do a multi-class given an object, I want to figure out what it is, you would still be using an activation function that is sigmoid, but your outcome will not be one single. So in terms of programming, the one that you have output is called as the dense layer. Your dense layer would essentially not be just one.
Yeah.
I don't know if I answered your question though.
yeah, maybe we can take it
Yeah, we
outside.
can take it out. Yeah.
I think just coming back on what she said, the main difference is that you can have a
nonlinear decision bundle.
Yeah.
Multi-layer perceptron.
Yeah.
Right, right. It's non-linear.
Yeah.
Okay, so
Any other questions? We move forward? Okay.
so all of you have the setup ready with you. Have you cloned the repository? Yes?
Is there anyone who have issues cloning? Yeah.
So once you install clone the repository, the prerequisite is you need Anaconda. And once you have installed Anaconda, you'll have to do a pip install Keras. So unless you have Keras, you'll not be able to run the hands-on.
How many of you here don't have Anaconda installed? Okay.
Okay. So for people who have Anaconda installed, all you have to do is pip install Keras. Keras. Keras.
Keras is a package that internally uses
Theano.
Theano as its backend, and the beauty of Keras is if you don't want to use Theano and you want to use TensorFlow, you could still do that. So it's an abstraction layer over what backend you can use.
So you can just specify what your backend is, Theano or TensorFlow, and then you can just use. So people who have used scikit-learn before, Keras is very similar to that for deep learning. So let's open the, I think you'll have to open the data folder and unzip the auto.tar.gz. So untar it and unzip it, you get the data set. And once you have unzipped it, then you can run the notebook. And then come back to multi-layer perceptron notebook. Yeah. Does anyone have problem, or do we just continue? Okay, let's continue. So we have the multi-layer perceptron here. So we do a bunch of imports here. We use Keras. And we are using the auto data set from Kaggle. We read the train and test data. And this is how the data set is. This is anonymized data. We have 93 features and then a target, which is basically your class of product. So is it class 1, class 2, class 3, and there are 9 classes. And we have 61,000 rows. And we need to convert the target column here in the data frame to a categorical format. So we just do that. Then we create a new label column using the categorical one. So now I don't have class 1, class 2. Rather, I have 1, 2, 3, 4, so that I can feed it into the multi-layer perceptron I'll build. So the class numbers are 0 to 8. I just drop the ID column and do some stuff there. So now I have the y integer here. So what I do is Keras has a utility function which will convert that into categorical data, which is of this shape. It will basically do a one-hot encoding. It will expand it into 9 columns, which will have zeros and ones there. And here is where we build the multi-layer perceptron. So this is a sequential model where we place different layers one after the other. So model is equal to sequential, which is coming from Keras. And then I say I'll add a dense layer with output dimension 64. Input dimension is 93, which is x shape of 1. And then I have an activation function of tan h. Tan h is basically will give you -1 or 1. And then I again add one more dense function. And activation here is softmax because now this is a multi-class problem. We have softmax. Yeah. We compile it. We define the loss function here because it is a categorical value. We have categorical cross entropy, and our optimizer is a simple SGD. And once we have all these things, we compile the model and fit the model with our training data, which is X and Y. And here NB_epoch will tell you how many epochs should I run this for. So one epoch is, as I told you, one forward and backward pass. So we do 5 of that. And to do stochastic gradient descent, the batch size is 128. And then we just run it. So if you see, the first one itself gives you an accuracy of 0.64. And then as and when the epoch increases, the accuracy keeps increasing. This is because whenever an epoch happens, there is more learning and there are more correction to the weight, and it goes closer to reality. Now you can go back and increase the number of epochs or change the dimension there. You can change the batch size, you can change the epoch and try it around. So for people who are trying it here, you can just change these values and try it. Yeah, so from 5 we make it 10 and then run it. You see that the accuracy keeps increasing, but after a point it will hit threshold and it will not increase. So you can just play around later.
And it couldn't work. Okay, so how many of you actually ran this? Oh, okay. Awesome. The notebooks stand for itself, and this was just a small demonstration to show how MLP works. I think if you guys can't compile it or run it here, you can always go back and install the required packages and run them. And if there's anything, you can always write to us to understand what they do. With that, we continue?
Yeah.
Do any of you have questions? Yeah. For the dense?
Okay, here?
Oh, okay.
Here, right? Yeah. So I wanted 64 nodes in the next hidden layer. So it's a random value I gave, and it worked for me.
Yeah.
I did see that problem when it was on the website, and I was just wondering, the 10 version that you've just run there, which looks to be like maxing out.
Yeah.
Where does that sit with regard, like to the leaderboard in terms of what was actually achieved on this problem, if you know?
Sorry?
Where does it sit roughly on the leaderboard?
Oh, on the.
Just
Oh,
roughly.
oh, we never
we
pushed this.
We have not submitted it.
We
We have not submitted it.
Yeah.
We just took the data set
Set
and then
and
we ran it. Yeah, but a lot of people are already using Keras for this. And I think the creator of Keras, he himself has posted a lot of code using this package.
And I think the one that's sitting on top of the leaderboard is an ensemble of machine learning models more than deep learning.
Yeah.
Yeah. Yeah. Yeah.
Oh, this one, accuracy? The different metrics, huh? So you can just refer to the package Keras. You can go to keras.io and it will give you what are the metrics you want as output. So this metrics just tells you what is the output you want. For us, we need accuracy, and that is where it is telling you this is the loss and accuracy. So you can try out different things there.
Okay, so one thing is after you run a lot of epochs, the model's accuracy does not increase. And there's something called as callbacks, and it usually, if your value loss is like it's not changing after a point in time, even if you've given more than 100 epochs, it stops after it things don't change. So the only idea here was for us to start seeing accuracy so that we know how good the model is after you run X number of epochs. And there are multiple metrics that you can pass into them. Yeah.
We move on to the next one.
Yeah. Anything else? Any other question? Okay.
So one thing, one problem with artificial neural networks is to quickly overfit when you have small amount of data. So if you have hundreds or thousands of data, there's a high chance that you'll be overfitting. And there are some ways how you can overcome this in artificial neural network. You can do a weight decay or L1, L2 regularization, or the famous one is dropout. So one of the artificial neural networks is there for a long time, but then from 2010 it has been picked up like crazy, and the reason is the invention of dropout. So what happens in dropout is you have all these connections, and when you're training the model, you randomly remove the weights. And when you randomly remove the weights and run it, people have observed that it is not overfitting and it actually works accurately. And there's no reason actually why this thing works, dropout works. Jeffrey Hinton, the father of deep learning, he actually says dropout works, but there's no reason it works, and that is the active area of research.
Yeah.
Are you dropping out a low weights or just literally?
No, it's just randomly removing. It's just randomly removing the ones.
And then the others, the remaining connections adjust their weights.
Because it's once you randomly remove and there's a back and forward pass, and then there's an error, you again realign the weights.
Yeah.
Yeah.
So just you're actually removing some of the input. Oh no, sorry, hang on, I'm looking left to right.
Yeah.
I was thinking some of the inputs probably.
No. Oh. Someone else had a question? Okay.
Okay, now we move on to natural language processing.
Yeah. Okay, so before I start talking about natural language processing and get into deep learning, how many of you here have done natural language processing before? Wow. Okay. What were you guys doing? I mean, what did you use and anyone?
NLTK?
NLTK. Yeah. What, sorry?
Word to back.
Word
Okay.
to vec,
Okay. Okay.
Spacey.
Spacey.
Okay.
Hmm.
Stanford core NLP.
Yeah. Okay. Okay. Anyone else did anything apart from the libraries? What were you actually using it for, and what kind of approaches were you looking at? Okay. So I'll go ahead and I'll start talking about what are the different approaches for natural language processing before we get into how deep learning is used. Okay. How many of you would be amazed if you could have a machine cough up new recipes, right? And but the problem here is if you actually look into this, it says cut the beer into cubes, right? A machine would generate a recipe, no doubt, but the problem is, does the machine understand what is the idea behind this generation and what is the essence behind it? So before we get into understanding how this works, let's take a simpler normal approach. So current NLP, or mostly what people do with natural language processing, is you have your inputs and then you extract your features, which is term frequency multiplied by inverse document frequency, or you do a bag of words approach, and then you have a machine learning model, which is your softmax or your support vector machine, and you start predicting how good the model is. But if you really work with natural language processing, the biggest problem is you're expecting input to be right. In the sense, how many of you here have used Wren and Martin or know what Wren and Martin is? Okay. What Wren and Martin is a book which gives you the rules for, it's basically a grammar rules. And the biggest problem with natural language processing is you're expecting the input to be grammatically right. You're expecting the words to be present in the right position. But if you're solving a real problem, that is not how it works. You have a sentence, and sentence has noun phrases, verbs, adjectives, everything put together. But in this world, if you see most of the Facebook posts or Twitter, which allows you only to use 140 characters, you see that people have started using short forms of words, and people are not really caring if the word's grammatically right. And when you're trying to do any social media analytics or reading blog posts, you're assuming it to be right, and your model assumes the same, and things break. So structure is very important, but it's very hard to know that the structure is right. Like, for example, a small crowd quietly enters the historic church is not the same as a historic crowd enters a small church. It's just the movement of two words, and the whole context changes. How many of you know what sarcasm is? Right? And if you're solving anything related to sarcasm, it's very hard to capture any sarcasm, even for humans. There are lots of people who can't capture. Sometimes I can't either. So simple thing is representing structure is hard. Representing structure is very hard because your vocabulary is big, and your vocabulary keeps changing. Like 20 years back, people probably spoke a different dialect of English than most of us do, because our English mixed up with a lot of technical words, and there are words that don't even exist. Like, for example, if I'm talking about a scalable system, scalable is not actually a word that's there in the Oxford Dictionary, right? And so over time, your words, your n-gram starts exploding, and representation of structure starts becoming harder and harder. So we have a lot of limitations with the current architecture for doing natural language processing that's widely followed, and people are changing now. The thing is, you have fixed sizes of input, and then you have fixed computational steps, and you would see that 2-3 years back, the only thing people were trying to do was they were trying to build rules and see who is an actor and try to find a whole lot of relations with the actor itself. And again, that started becoming a very big problem because your n-gram started exploding and you didn't really understand context. Now, before I go further and see how we can solve this step by step, any idea how this can be solved? How do you solve or understand structure without the structure not really being present? I'm sorry? Okay, before we go so deep into the neural, simple, what can we do? That is a more simpler approach of, yeah?
The string is often present where another string would be, so we realize that WD is where would be, so WD and would probably have something in common.
Like a co-occurrence matrix. Co-occurrence matrix, yeah, that's one way. Any other? Okay. There's no one single solution. There never is. There's one way of solving this, and this is called as vectorization. How many of you here know what vectorization actually means? Okay. What is vectorization? The ones who know. I'm sorry? Vectorization in general. Generally, what is?
Turning information into a vector.
Yeah. So exactly. So you turn information to a vector, precisely. So you're here in natural language processing, you're converting text into numbers because computers understand numbers better, and there are different ways of doing it. One is called as one-hot encoding. The other ones. So what you do with one-hot encoding is you take the position, the index of the word, and you just encode it based on however bigger the dimension you're looking at. How many of you here have used WordNet? If you use natural language?
one,
Yeah.
two.
Okay, so WordNet is this huge library where previously, I don't know if lots of people are using, I think they are. What you could, if you gave WordNet a word, it would give out all the synonyms for the word. And there are so many different things in WordNet where every day it's getting updated, and it's like a huge dictionary with reverse mapping for different things. Now, do you see a challenge in maintaining WordNet? What would be the challenge if you had a huge dictionary? Yeah.
You get, like the associations change with respect to time, like you were saying.
Yeah, and maintaining this manually is a pain, right? And then there is co-occurrence matrix, as he mentioned, where if there's a presence of one word with the other word, then you say how good is the co-occurrence of, let's say, food and, let's say, pizza. If there's a sentence with food and pizza coming all the time, the co-occurrence of pizza with food would be very high. But at some point of time, these things fail. Mainly because in one heart, you're really not considering the context. The context of using words with different sentences mean completely differently. And WordNet's really hard to handle because someone has to manually go update and change relations, and over time, nothing manual things break. And the co-occurrence matrix, the biggest problem is if you have a billion words, then it's a billion cross billion co-occurrence matrix. And even if you have to change a value of one single word co-occurring with the other, the computation is very high. So we overcome this with a concept called as word-to-vec. Any of you heard of this before? Wow, awesome. Okay. So this was something that was released by Jeff in 2010 by Google, and what they're essentially trying to do is they do a window-based vectorization where they are vectorizing a word, if I may, by considering the words around that particular word, and the words vector keeps changing based on different places it occurs. So what you solve with this, which was lacking in most of them, was here you don't really care about grammar. You don't care if the structure is right because you're not really parsing it against a structure. You're just giving the emphasis for the word and the presence of other words around it. And based on the surrounding words, the model starts learning and picking up vocabulary. So you don't really need training data for something for the model to run. The model starts learning by using the data that it's given. And different domains have different data sets. So whatever data you feed into the model starts learning the language. And at any given point of time, one vector represents the discrete state of the word, right? And so similar words are glued together. So this was something that they didn't anticipate would happen with vectorization, with word-to-vec approach. So when they tried to solve this problem of when you searched something on Google and they wanted to give you searches that meant closest to what you searched for. And the biggest problem with that is whenever we search on Google, the problem is we don't really search with grammar. So structure was becoming really hard for them to understand. So they wanted to try and see if you had words and when you vectorize them with windows, do the same words sit together? And they realized after word-to-vec and they ran a lot of operations, they realized that most of the similar words are clustered together.
So how many of you have an Android phone? And how many of you like the next word prediction there? It is actually built on top of word-to-vec.
Word-to-vec. Yeah. So so it's reading your context that you've typed before, and it predicts what the next word is. So it does it with two different, it can predict in two different ways. One is called as a skipgram, where if you take the context word, which is learning, it vectorizes learning based on a window of context around it. That is, it would consider an efficient method for and high quality distributed vector, and it would vectorize learning in this statement based on those surrounding words. This is one approach. So given learning, so the outcome of this approach is given the word learning, it will predict the surrounding words around it, right? And the next one is called as continuous bag of words, where instead of trying to give a context word, you try to give a set of words around a particular word, and you want to try and see if it can predict what you're looking for. And if you're interested in automating email, like sending off emails or writing emails, this is wonderful, because if you're pissed off at your boss and you want to use diplomatic words and you can't really find any, you can type a statement, build a model, and you can give the bag of words to the model and it'll tell you what is the word that you can probably use. Right? Yeah, that's awesome. And this is one way of doing it. So this is both of them looking, both of the models next to each other. So in your continuous bag of words approach, you're trying to predict a word based on a set of words. And in skipgram, given a word, based on the words around it, you predict the words around it. Yeah, so I think we've taken a very interesting data set to show the power of word-to-vec. If you can, yeah.
So go back to Jupyter Notebook and...
yeah, sorry.
Just quickly for also fairly novice, but I used n-grams before.
Yeah.
And there you also try to look at, let's say, 4 words next to each other.
Yep.
And here you seem to do something similar.
Yeah.
Look at the environment. Can you give us some insights about how these would be related?
Okay, so in an n-gram approach, what you're still trying to do is you're going one word after the other and you have n-grams next to it, but you're not really taking the whole around the boundary around it. Like, you're not taking its neighbors on the left and on the right, one. Secondly, when you take an n-gram approach, you're not really doing vectorization. You're not representing a word by the words present around it. With n-gram, what you're really trying to do is you're jumping your windows and you're trying to see if something makes sense. So if you've ever done entity extraction, or you would basically have pause tags for a word, which is the structure of the statement, which says parts of speech, and then you would slide your window to see which is your now named entity and what are your verbs. But the problem there again is structure. So this bypasses structure because it's learning based on the data that it's given without really caring what language it is. And this is what the power behind this. Another amazing thing is, no matter which language you use, if you're trying to translate a statement from English to, let's say, Spanish, because the words are supposed to are related to each other based on the words surrounding it, you can actually get the Spanish word for whatever you mentioned in English. They'll all be sitting together in the same cluster. So that's the beauty of word-to-vec, because you're vectorizing based on the surrounding words. Any other questions? Yeah.
Can you give me an example of what that vectorization is? Because I'm having difficulty figuring out what that vector represents. So for example, is it for learning?
Yeah.
There exists, a vector of 100
Dimension.
100 elements.
Yeah, okay.
That represent like 100 different words and their likelihood of appearing next to them. Is that it?
Yeah. So what it does is, if you take learning, so when it comes across learning for the first time, based on the words around learning, it would have built a vector. The second time it comes across the word learning, it looks at the words around it and it sees what has changed and what has not. So slowly, if you have a bigger corpus, then you will see that learning is vectorized based on the presence of different words that come next to it.
So basically try to get the probability, given the current word is learning, what could be the surrounding words? Okay. You find the probability of that.
How big is that vector? Is it
So you define the dimension of the vector. So you can say, I'm looking at, I only care about 5 words before this, before my context word, and 5 words
after. So there
after.
are 2 things. One is the window size and the dimension as well.
Yes, I meant the dimension.
You can define it.
You can define
so
the
Will then it be constant across all of the words?
Yeah.
Yeah.
Yeah. Did I answer? Yeah. Okay.
Cool, thanks.
Okay. Hey.
Yeah, so further to that question, so is it like, say, if you define 100 dimensions for a single word, so that is a fixed size for another word, and after training you have so still this 100 dimensions, but different weights stand for that word, and so in that corpus, the different words will be kind of different dots.
Yeah.
And how do you, so when you are doing, for example, that word prediction,
Huh.
If you find one word, so you see one dot in that multiple dimension.
Correct.
Do you just look for its neighbor dots once you train the?
Oh, so you do something called as cosine distance, where you
based on distance, you just find next word.
the ones that are closest to it, because everything's a vector. So cos of 0 is 1. So the distance between because you're representing vectors, the distance between two vectors, if they are a minimum, the distance is minimum, then they are more similar to each other. And because each vector is is a discrete state that it represents of that particular word, you see that similar words are grouped together because their vectors look similar.
And because you have a higher dimension, let's say 100, a word can have different states. So let's say a word bank. Bank can be your river bank. Bank can be your institution bank, or it might be a sentence where I say, I am banking on you. So bank has different meanings to it. And because you're in a higher dimension, this word can be represented in different formats. And in each dimension, it has a probability of going with the next word. So basically, when this entire window-based vectorization happens, it actually learns the relation between the words too.
Yeah. So when you're predicting it, you're looking for the closer in terms of the cosine.
Yeah.
Distance. But say after you type in the second word,
Yeah.
what do you do?
You take the context of both of them, the words before, and that's your window, right? So you're taking both, your vectors for both of them, and then you predict the next one. So if you look at the continuous bag of words, you have different words, and you took vectors of all of them, summed it up together, and when you do a vector summation, it gives you the closest vector that it matches to for that summed vector.
It again depends on what corpus you have, what vocabulary you have.
Any other question? We can move on to hands-on. Okay, I think we'll just quickly move through the hands-on. We still have to show deep learning because, yeah. Okay, there's another library that you guys have to install. It's called as GenSim, and it's by.
I think it is part of Anaconda. Yeah.
Okay. Yeah, if it's part of Anaconda, it's awesome because it's a very good library to do word-to-vec. I think we just run through. Okay, so how many of you here know Shakespeare's plays, Julius Caesar and Macbeth? No, not bad. Have heard of? Yeah. Okay, so we've taken Julius Caesar and Macbeth. We downloaded this from Gutenberg. Yeah, Gutenberg, and then we're trying to make sense of characters there's no training data. The data are these two plays. And we're trying to see if we can find relations between characters. Okay.
Characters as in characters in the play.
Oh, characters in the play, I'm sorry, not alphabet characters, yeah.
So we just take the data set, we do a bunch of cleaning.
Yeah.
We remove the stop words. So these are the sentences there.
Okay, so what we're doing here is we're building a word-to-vec model, and we are providing the corpus as the sentences from both Julius Caesar and Macbeth. And when we are telling that retain the context of words of just length of 5 windows, length of 5, and size is that's the dimension. And we have 4 workers, so they can run in parallel. And the minimum count is when you consider the window. I'm giving a frequency that this word has to occur at least 5 times. So that's the parameters.
So basically, this is the vocabulary the model has now.
So 1 has occurred more than 5 times, so it sits in the vocabulary. Yeah. Okay. How many of you here know what TSNE is? Okay, so for others, what TSNE is trying to do is because we have represented a word in 500 dimensions, you can't really visualize something in 5. How many of you can visualize beyond 3 dimensions?
And plot it on a computer.
And plot it on it. Okay, yeah, I can't. 2 dimensions hard for me, so 3 dimensions like really, really hard. So what TSNE does is it's a dimension reductionality, and it reduces from your x dimensions that you have to something that you can represent in a two-dimensional plane. So what we are trying to do here with the TSNE model is we are trying to represent a 500 dimension vector and try to see if there are words that are similar to each other that can be represented in 2 dimensions. Does it show? Yeah. Okay. So this is our model, and this is how it's understood. So I don't know how. So it sees that bed and speak are words that sit next to each other, and there is there's honest and there's while that are very close to each other based on what the data that we fed. Looking at this, it's just trying to see if the words are grouped together, but the real power comes next when you can do analogies. So how many of you know which character belongs to which play? Because Duncan is a king, is a duke of Scotland, and Caesar is Caesar. So what we are trying to see here with this analogy is if Duncan is to Scotland, Caesar is to which place? And prior to this, we've never mentioned any rules. We've not fabricated the data to show results. And just based on the vocabulary that it's learned, it's trying to build relations based on the word's presence. You see that we were actually, the way it's understood relation is Duncan is related to Scotland. It says Caesar is as related to Brutus, right? And if you look at, so I think Duncan was killed by Macbeth. I don't know. So Duncan and Macbeth were related in a way, and we're trying to see who Caesar is related to. So Caesar is related most to Lord. So a lot of people are calling him the Lord. And then the very next that Caesar is related to is Brutus, right? And we're trying to see the same with another character called as Banco. Right, so these are analogies. So this was something that people never really realized when they built Word2Vec, because this was not what Word2Vec was built for, and this was like a side product which even amazed the people who built this. And so if you look at the last statement mod, so what we are trying to say is if we give 4 words or X words, what is the word that does not belong to the context of words that we give? So Duncan, Macbeth, Banco are characters, and Scotland's a place. It's able to understand that Scotland is being used as something else, considering the other 3 of them. One thing that we can show is we've taken a window size of 5. Something that guys can go back and run is if you take bigger windows, bigger dimension representation, how do your analogies look like? And if you start looking into the articles that are written, one beautiful analogy, if you give it Wikipedia corpus or Google billion token corpuses, if man is to king, what is woman to? And it says queen. And there's absolutely no training, and it learns based on the positioning of the words and the context behind it. Yeah?
You know the word window, are the positions special in any way, or is every positioning treated in exactly the same way?
Every position is treated in the exact same way.
It's not like one word comes before another, therefore it has a slight different meaning if it comes after.
No, it doesn't. It's not caring about structure. So that's the beauty. So even if you miss words, or if you're representing them in a slang way, it still doesn't matter because it's not looking at structure. It's vectorizing based on something that's present around it. And that's how it's able to pick relations.
And also you don't need something like WordNet where you keep on adding words. You can have your own dictionary because a financial language might be different than technology or a normal English. So it's very hard to have WordNet there. But if you use something like this, you just feed the data and then you have already built the relations.
Right. Any other questions? Because we still have deep learning to show. Okay, so another thing with WordNet, this is shallow network because it has one single layer, one single neural network layer, and it's already being widely used. And if you can go back and check, you'll see lots of usage, and people are trying to do a lot of wonderful things with Word2Vec. If there's anything else that you want to talk about Word2Vec or NLP thing, we can probably take it offline. I think we probably have 20 more minutes. We'll do the deep.
So now we go back to neural networks, the recurrent neural networks. So whatever we have seen till now is only feed-forward neural network. So we saw data moving from left to right, and there is no loop anywhere. So this is what we saw, right? That was horizontal, this is vertical. It is just one way of movement, and there is no feedback. But then there might be interaction between the hidden layers here, or there might be a feedback loop here from the hidden layers. So this is called recurrent neural network. The only thing special here is there's interaction in between the layer itself, the hidden layer, and there can be interaction across the layer. So this is one-to-many sequence where you have an image and you want to explain what it is. So you give it an input, you give an image, and you want to find out what are the objects in the image. Yeah, and then you can have many-to-one sequence where you give multiple input, and then you want one output to do sentiment analysis. Or you can have many-to-many, like Nischal suggested. You can have a machine translation where you have English to Spanish translation. So how many of you have used the Google Translate app? Yeah, it's wonderful. So all you have to do is open the app and show up a board or something which is in Spanish. It automatically converts the text on the fly to English, and that is made possible only because of neural networks and recurrent neural networks. So basically, this is the structure of recurrent neural network, RNN. You have an input X, you have a single node, there is a feedback here, and then you have an output. So it is nothing but you can easily unroll it and say it is the same thing, but over time it is just moving forward. So the input of the second one will be the output of the last one. So over time, you get the input from the previous pass on to the next one. So this is about recurrent neural networks, and there is one special kind of recurrent neural network called long short-term memory, LSTM. So the problem with recurrent neural network is, let's say you have a movie going on, and there is some amount of information which was not just there 3 or 4 words before, but it was specified during the start of the movie. Let's say a character, Duncan. Duncan is a male, and then you want to use the next word. Should it be he or she? You don't know. That depends on the gender there. So that cannot be done with a simple recurrent neural network. There were problems because there is no memory there. Yeah, it just gets the output from the previous layer. Then they figured out you can have something called as a LSTM layer, where you have a memory layer inside every node. So what this does is, it might look complicated, but then it is fairly simple. There are 3 parts to it. The first line here, then the middle part here, and then the output here. So
how many of you know what gates are, or AND, NAND, NOR, XOR? So that's precisely what it's doing.
So it is basically combination of the gates. You have AND, OR. Then we use our activation functions, sigmoid, tanh, etc. And then each cell here, each node has a cell state. So what this does is, the layer on top, the line going there, will help us to maintain the memory. So that controls how much of information and how much of memory should be passed on to the next cell. So you can have your gender information always running through all the cells, so that you know Duncan is a male and the next word should be he, and in Spanish equivalent of he, there is something. So you can retain your knowledge using the cell state here. So there are 3 parts. The first one is the forget layer here. You have the output coming in from the last cell state, last cell node. You have the input, new input, and then you run a sigmoid activation. And now this, and the output from this will control how much of the previous cell state should I remember to move forward. So if it is a 1, you will remember everything from the previous cell state. If it is 0, you don't remember anything. And because this is a sigmoid, you can partially remember some of them.
What do you mean by remember something?
So for example, the gender information.
So how is that encoded in, is it?
So there is always a cell state going. So there are two output. One is HT, but there is also one output, which is the cell state itself, the output of all the combination of these.
Encoded in what sense? Encoded in the sense, how is the gender?
Is it a number? Is it a vector? Is it a matrix?
Oh, so
Okay.
it's a
Yeah. So it's a number.
It's a number.
Basically a vector everywhere. So everything is vectorized.
all
So
those
before you feed it into a neural network model, the first layer will be an embedding layer, which is nothing but vectorizing your inputs.
So those arrows, are they all numbers or are they all vectors?
These, yeah, they are vectors.
Vectors.
Yeah.
Yeah.
Thanks.
So that is the forget layer, which controls how much of information from the previous cell state you want to remember. Then this is the major computation layer, where given the new input, what is the new cell state that is computed here. So you have the new input, then you run sigmoid, then a tanh, then you combine it with the previous cell state to give the new cell state here. And after this, now you have an output, you have a cell state, and then you give a combination of them to the next one. So basically, you have a long memory flowing everywhere.
Oh.
Yeah. So the problems with RNN is if you have a very small data set, then you don't get a good generalization and will end up overfitting, or you don't have good results. So for you to have good results, you should have the recommended is million by Google, but then not all of us will have such a big data set. At least tens of thousands of data points is what is recommended, not just 1,000 or 2,000. When you have smaller data set, you don't really get good accuracy. So let's just run through the notebooks for this. Because I have a laptop, we had to choose a smaller data set. We have a set of a block data set where we have labels, male author and female author. We will try to use LSTM and do a classification on them. We have around 3,000 data points, 3,000 blogs, combination of male and female. So let's see how it works. So do we read the data set? We do a bunch of cleaning as usual. Yeah, we do a filtration there, remove stop words, etc. Then we create labels for them. So for me, 0 is male and 1 is female. So I create a new label column. And what we do is for LSTM to run, it is not based on words, but it starts from single character. So it is very similar to how a baby learns to speak. It will start uttering simple syllables and then simple words. Then it will actually form proper sentences. So we are doing the same thing here. We have, can you scroll up?
Yeah.
So what we are doing is we build a dictionary of character to index dictionary and index to character dictionary. So given a character, let's say A, I know the index of it and the reverse mapping as well. Given 1, I know it is A. Similarly, we do the same thing for labels as well, a dictionary of labels. Here it is very simple because we just have two labels, two classes of labels, male or female. But then you can have a multi-class problem where you have 9 or 10, and you need an index for that, for the reverse mapping as well. So we say that the maximum length we will consider is 5,000 from a blog. So we are defining it here. And this method here is converting every block to a sequence of character, which will basically give us the indexes, which will be input for the LSTM layer. So now we have X and Y, which is nothing but the character indices. character sequence index, and then we have the labels here. Now we run a simple LSTM model. Again, it is a sequential one. We place the layers next to each other. Here is the embedding layer where we do the vectorization. Yeah, and we define the maximum length there. And we add an LSTM layer here where the input size is 32. Then we have a dropout layer to do some regularization, and then a dense layer of size 1, because I just need to know is it a male or female, which is sigmoid optimized activation. I compile the model and then give the test and train data there.
Just this will take a while.
So this will take a while. LSTM is computation heavy, and it takes a lot of time actually. When you have medium set of data, it will actually run for hours. And yeah, you can see it is running slow. It says one epoch will take 190 seconds approximately, and we have said we need 10 epochs. So 190 into 10, 1900 seconds.
That's not, we'll get kicked out. So, so with this running, what we'll do is we'll go back to the slides. And, okay, before we go back, any questions? Yeah.
Just quickly, just so people know, when you're going through the word to vec, you need to have Python 2 rather than Python 3, because Python 3 won't work without some tweaks.
Okay. Yeah. So if someone's using Python 3 to work with word2vec, you need to do some tweaks to get the whole library up and running.
If you want to know about specific cell, it's a cell 30, I believe, with regards to the filter function. It's basically taking some words, splitting them up, and just filtering out those words.
Yeah.
You just need to tweak the filter function, because otherwise it actually returns the function filter, and thus you can't use the model.
Yeah.
Right.
Yeah.
Thank you.
Sorry? Yeah. So if you're using Python 3, and if you're using word2vec, cell number 30 using okay, we can go back.
So we are using Python 2. So if you are using Python 3, you'll have to adapt to Python 3. You'll have to do some modification in cell number 30.
Yeah, sorry, I was 13, I think.
13,
One,
yeah,
three.
yeah.
Yeah, that's it, equal 12. So it's that filter line, words equals filter lambda
Yeah.
is true if
Yeah. So
Yeah.
correct. Yeah. So this filter function is differently, it's represented different in
Python 3.
Python 3. Using yeah.
Yeah. Yeah, go back.
Yeah. Any other questions on LSTM, RNN before we go ahead? Yeah.
So with these models, it's still important to remove the stop words like you would with a kind of non-distributed representation.
It depends. Like for example, sometimes stop words are important based on what problem you're trying to solve. But here, what we are trying to do with the different blogs is we are considering stop words don't really add value, but it actually might, because different people might probably be using stop words in a completely different way. The reason we've removed it is we thought we'll clean it and just concentrate on feature words that are non-stop and try to classify the gender. Otherwise, it depends on what problem you're trying to solve. Yeah.
Maybe I missed something, but given we're talking about words, why are you taking the blocks and chopping them up into characters?
Yeah. Okay. So RNN, like any other neural network, the problem is you have to let the model learn the words. You give it characters.
So it comes from bottom up.
Bottom up.
Try to fix the characters to get into words to get into sentences into a block. So using LSTM, you can actually give a good amount of data set. Let's say you have 30,000 blogs, and then ask the LSTM model to generate blog for you. So that is also possible. So initially, it will start outputting random characters. You can have a dot exclamation A/B coming. Then after, let's say, 10 epochs, or
run it for
depending upon how powerful your computer is and the data set, the output starts getting better.
So it learns like a small kid. That's the notion behind. Any other questions? Okay, we have one small topic remaining. The power of GPUs.
So all of them need a lot of computation power, and then people have realized that what matters is the flop cycle, the float operation cycle, and it happens that GPUs are very good in processing floating numbers, and CUDA, NVIDIA team has come up with CUDA, which helps you fasten your deep learning process. So even on AWS now, you get AWS instances powered by GPU, so that you can do all the deep learning stuff on the cloud.
How many of you played games on your computer, like or you played games
with
when you were
or
kids?
without seeing GPU? I'm sure that you would have seen a remarkable difference in the graphics.
Yeah.
So yeah. So CPU is small, but then GPU is focused on doing compute-intensive tasks. It has a lot more cores than a single CPU would have. So that is the reason people are now using multiple GPU or GPU clusters to do deep learning. Yeah, and this is one way of doing things, but there are also different kinds of hardware you can use. There is something called as what was that? Neuromorphic engineering.
That's a research.
Where based on the problem you're trying to solve, you come up with a custom hardware with all the neuron design, and that is much faster, and it uses less amount of energy comparatively. But then the plus point here with GPUs is it is a generic device. You can run any kind of, you can solve any kind of problem you want, but then the neuromorphic engineering is more specific to your problem, and that is an active area of research going on.
I think they're building some machines in Stanford research. The idea is with all of this, you're still trying to simulate how a human brain works, but the attempt they're trying to make with neuromorphic boards is they're trying to emulate a human mind, and they're trying to bring down the power consumption as much as possible by delivering more speed, computational speed.
And some examples of deep learning are video classification. Your in YouTube, how many of you have used the auto caption? So basically that runs on neural networks. So the input is an audio stream, and then it detects the text, what is the text of the audio, and then it gives you the caption. And now the caption can be of any language. It can be English, it can be Spanish or Hindi, it can be anything. And image recognition. A lot of fashion commerce sites are now using image recognition to do better recommendation systems. So you come up with better I buy a blue shirt, what kind of pants should I buy? So those are the things people are building now. And this is one famous example, image generation by Google Inceptionism. You feed it a lot of paintings and images and then ask the model to paint it on itself. And this is what you get out of that. Then you can also do a handwriting generation. Yeah, so there are endless amount of application there.
And all these slides, everything will be available on the repository. We'll just push them there.
It's there on speaker deck, and all the code is on GitHub. Any questions?
Yeah. Okay, we're done.
Yeah.
Any questions? Yeah?
Yeah, he has a question.
Yeah, sorry.
The weakness of RNN?
Sorry?
So the thing with RNN is it's based on neural networks. You can have a better solution for your non-linear problems. But the only problem with RNN is it cannot remember memory, and that was solved using LSTM. And there's one more concept called as GRU, Gated ReLU Unit.